One of the core problem of large language model that I've been literally yelling about for 2 years is the high quality long context bottleneck that they have. It is truly difficult to train LLM to handle large context without any loss of performance. Anything larger than having a 250K context window will start to show sign of deterioration of intelligence. Even the current frontier LLM will only have an effective high quality context area of around 40,000 token of size for moderately hard problem. This is why I got unreasonably excited about the release of the recursive language model by Zhang earlier in 2026. I truly think that this paradigm will be the one that we'll see more in all our favorite agentic system this year, and will yield truly magical improvement in intelligence without much added cost and training. In a nutshell, the RLM is a technique which lives more in the family of harness method, in which we put the LM inside some sort of environment to do a task. In our case, the main goal of the environment is to allow the LM to process large amount of context without retraining the model and without loss of performance. For RLM, this environment or harness is a read eval print loop or REPL system that can be best visualized as like a kind of Jupyter notebook thing. The core idea is that instead of loading all of the context inside the model directly, you load it into the environment, and then you give tools to the LM of your choice, doesn't matter which is it, to mine the information in that pile of context. The magic of the RLM is that on top of that environment that allow it to effectively have high quality context in the millions of token range, it also allowed the LM the possibility to kind of spawn like a sub agent to do some semantic subtask in the REPL environment. Hence the name recursive language model. What we're going to cover today is the full theory about how the RLM work, using the information from the academic paper and the blog post from Alex. We'll also chat with the first author directly about what's the core intuition behind the method and what's next in this paradigm. I hope you'll enjoy. And also, after this video, if you want to go more into the practical aspect of RLM and get kind of hands-on the material, I highly recommend this video that my friend Neural AVB did on the subject. It's an awesome channel that goes in depth on very technical deep learning topic. You should check it out. Let's get into it. So the paper we're going to review is the RLM paper. You might have seen it float around a bit. Honestly, it's a great one. Like I really liked how it was written, and I really liked just the general flow of it. And basically, it's kind of a harness paper where it shows like a new way of plugging an LLM into like a long context type of harness, so that they can actually have like ingest more context without having the context rot problem. So overall, it's great. It's a lot of pages, but like what matter more is like the first 8 pages, right? So it's not like a terribly intimidating paper to read, but what is cool is that they added a lot of information about like what didn't go wrong, what did it go right, like all of the qualitative information about literally what's up with the RLM as it goes and ingest the context in different situations. So no, it's a pretty nice one. We're gonna be able to check this out in its entirety. So this paper actually comes from an idea that was like postulated in October. He has been actively working on it and refining the idea, and now we have a paper that was written, and it's exactly like the blog post, but like just pushed a bit further. So if you actually want to understand a bit more also how ideas in research are formed, take a look at the blog post, because it's much more raw in like the intuition and like what went into his head while he was thinking about like long context, and what he followed in order to like do the actual bigger experiment. And you see like what scaled from here to here. So it's pretty cool. I suggest you to read both, right? One for the intuition, one for like the rigorousness of how it's written, but it's very approachable. And this is a long context paper, right? So it deals with like having model ingest much more context that they can theoretically ingest normally, or they can ingest it normally, but there are on the frame of the context window where the context is kind of deteriorating a bit, right? You most likely already encountered this when you're like, I don't know, chatting with ChatGPT or whatever it is, and then like as the discussion go longer and longer, it just get dumber and dumber. So the intuition here is that like what you do generally is like you can summarize the information here, or like you take two chat windows and try to kind of like merge them into like a bigger one, and you try to distill out some of the information. It's kind of this idea, but coupled with a fact about LM, which is they're very, very good at coding, right? So like that's kind of the core intuition here. And what they did in order to like ingest even bigger context that the window allow is very interesting. They put the prompt that is absolutely massive in some cases, like 10 million token, inside an environment like variable, right? In a REPL setup, right? So the prompt that is gigantic is there, and then the model doesn't have it. It just kind of dig into it again and again through like this type of workflow, right? Where it's like digging into it with like, let's say, print prompt, like the first 100 lines or whatever it is, and then you're gonna continue like this, and then you're gonna slice it up a bit in a Jupyter kind of notebooky way, right? Where you have the data set and then you kind of play with it to understand it. It's kind of the same idea. And what is interesting is in this case, it can actually kind of delegate some of the tasks to another agent, and the agent will have a prompt and then will be able to interact with the same thing, right? In different way, but you have a subtask, right? So here it's like in chapter 1, find all items that are listed to belong to whatever, right? And then the LM will do it, and then it will return the response, and then it will do this back and forth. It doesn't do recursive like this, right? With the depth 2 or 3 or 4, but it do like a depth 1, and then it come back to the main root node, and then it at some point it need to kind of give a final answer, right? And this is all happening in a REPL environment. So the information is getting stored into a variable that is getting created here, like part 1, part 2, pre-kata, post-kata, whatever it is, right? And it will just like use these variables to understand like, okay, this is what is in this variable, so then I can use it. I can create for loop, can create a whole bunch of stuff. So it's really like free-form coding that is happening here. And at the end, it put a response, and that's it. So this big thing is the RLM. It's the LLM with the environment that is attached to it. So that's just a bit. And like if you look at the performance, it's actually pretty interesting. If you look here, and there's a tree here that has shown the a needle in a haystack here. There's the oolong, and then another version of it that is a bit harder. So this one is like linear complexity. This one is like quadratic complexity in terms of like length of the prompt, right? So it's much harder, even though it's like the same amount of input. And GPT-5 here is good, like a needle in a haystack, because I don't know. It's not like, yes, it's a lot of context, but it's not complicated. You can just do one scan through it and you're done, right? These ones require like doing a lot of computation, but you have to do it in one pass, which is hard. When you take the same model, so not post-train or anything, and you put it into the RLM harness, what you get is still needle in a haystack is good, but it's even good outside of the context window, which is super interesting. Like it's past the theoretical limit of what the model can ingest, which is, let's say, like, if you've seen my stuff for the past year, I've been talking a lot about quality long context, because I really think that like if you can crack the quality long context problem, there's a lot of stuff that becomes immediately available, right, to the models to be able to do that are a bit more complicated. And this seems to be a way to do it for free, almost, right? There's a cost associated to this, but it's not crazy. This whole region that was not possible before is now possible, like all of this, right? And on top of this, if you look at the curve, they're just getting straightened up throughout, right? So the O long is getting better, and the O long pair, which is like quadratic in like complexity per input length, is also doing great. So at 1 million, we're still good, and then I think they pushed it to 10 million, which is insane, right? And it's still working fine. And if you look at the average API cost here for this figure, it's not terribly more costly. You see here the RLM GPT-5 on long pairs. So this one is like kind of scaling a bit like this because it's quadratic in complexity, so it has to do a bit more processing. But it's possible at this regime over here, which is like just impossible for the other ones. And then like the other ones for the RLM on along, it's still doing super fine, while these ones, the GPT alone, are struggling a bit. The GPT alone are cheaper, right? But for a lesser performance here. So it is more costly in general to use that stuff. Things get a bit murkier over there in a smaller context, because like technically you don't even need to do sub-agent call or anything like that. The LLM can just like answer straight up. But this is just to show that like, yes, it's more costly to do this, but also compared to the other method that we're going to see, it's not terribly costly. So it seems to be a paradigm that makes a lot of sense. So we have here, from what I understood from the paper, basically attach more LLMs on the top of the main one and use them as storage. Kind of, but it's a bit more complicated than that. Like, yeah, the main storage is really this, right? It's this environment that you have running on the main node, right? But then you can spawn agent to like just do something, right? It's not like, I mean, you can call it agent, but it's like literally like just another RLM, right? And this RLM could do stuff, right? Like it has a REPL, and you can like do some analysis and work on there. So that's kind of what's going on, and you can spawn them at multiple points and then aggregate their information in various degrees. So that's kind of what you get on this front, and it's kind of like sometimes like you could in some cases they could not spawn the sub-agent, and in some instances it's actually better to not spawn a sub-agent. But in other cases, if you have to do some semantic search type of stuff, right, or like semantic understanding, you're much better to delegate it to a LM, and the LM might just like take the information and just ingest it and then just do something with it. Yeah, so that's kind of the element. And if you look here, you see here, it split the prompt on chapter 2, part 1, part 2, and it feed this the context of part 1 in it, right? You see that? So like it is like have a tighter slice of what it's gonna look at. So it's more like sub-processing of the information and storage. But then after that, you kind of take all the information and you put it together. Yeah. So this is a general idea. If you look at the long benchmark that they're using, right? For those that like maybe not familiar with long benchmark, there's not terribly a lot of them, right? And it's not just about like having massive tasks. It's also about like having tasks that are a bit more complicated, right? If you have like a bit more complicated task, then like let's say it like you will actually be able to understand a bit better how the models are handling it. Because if you look at it here, like all of these tasks have the same amount of input context, right? This one is much easier. It's kind of like constant, right? It's never harder that much. And this is why you see like Llama 4 Scout being able to do it with 10 million, kind of like, because it's an easy task. But as soon as you have like a bit more complicated task, it's a bit more difficult, and we have even more difficult than them in the benchmark used. We have the Browse Comp Plus, right? So Browse Comp is a benchmark for browsing agent, and then what they're doing is that they're actually augmenting it, right? So they're augmenting the Browse Comp like a corpus here with information that is a gold, right? That is being retrieved by O3 over there, right? And that is human verified, and then information that is kind of like noise, right? Which is information that makes sense in some way, but that is not the information that you need, right? So you have these R negative, and then you have this gold kind of information all piled up into like the browse comp benchmark. And then this is what they're using in this specific case. And you can go up to like, here they're using 1K document. The benchmark provides a verified offline corpus of a 100K document that is guaranteed to contain gold evidence and R negative document for each task. And then you have like a whole bunch of tasks. But we are using 150 randomly sampled tasks as our evaluation set. And then we provide 100 randomly chosen document to the model. So 100 doc is given. And then there's a bunch of tasks that need to go there. And once you give the 100 document, it's guaranteed that there's a gold evidence in there so that they can actually do the stuff. So this is a bit more difficult than this one, right? So there's some gradation of difficulty here. Then we have Oolong, right? And Oolong is, there's a whole bunch of stuff, document, and then you have to piece the information together on all the document. It's not like, it's not just you're gonna find it in one doc. It's gonna be like, you have to piece information together in multiple stuff. Here's the same thing with, let's say, like this transcript of like 12 hours of dialogue in this whatever game, right? So that's Oolong, right? And then they decided to kind of make it even harder with, so they split, they manually modified the 3-course split of Oolong to include 20 new queries that specifically require aggregating pairs of chunk to construct the final answer. So a task will be like this. In the above data, list all pair of user ID, where both users have at least one instant with a numeric value or allocation. Each one of the question can be labeled as one of the label, description, abstract, concept, entity, blah, blah. So like you have to kind of take pairs of information and like find them into this kind of mesh of information, and then you can output something useful. So a bit harder. This is supposed to be like quadratic in difficulty. And the last one is the long bench, right? V2. So the long bench is like, there's a whole bunch of documents that are long, that are getting there. We're data annotating them. We're gonna review their stuff. There's some revision that is being made. And then there's some manual review at the end, right? So it's like massive, mega big document. And you have single document QA here. You have multiple document QA. What is interesting for us is this one is the code repository understanding. So it's QA, 50 questions on like literally code repository, right? And then you have to kind of dig into this code in order to understand and answer a bunch of questions. So it's this slice that we're taking over there. It's actually like, it's a bit weird, but it's actually, I'd say it like, a bit difficult to make good long context benchmark. Even in the wild, like let's say you have the multi-turn types thing, right? You have like, there's a big corpus over there I need to dig into, but surprisingly there's not that much, well, at least there's more now, but like there was not that much like benchmark that already were structured in a way that you can test and train the models on. And also like it's maybe why some of the models are not that great on long context, because they never were trained with long enough context at all. The method is like this, right? Like this is the stuff. There's the REPL over there, the environment, hold the prompt, and then like it's loaded as a variable, and like you can play with it, and that's kind of that. Like so, like the context is loaded in a variable, and then the model has access to it, right? That's kind of the situation that we have here. You can spawn these agents, and the prompt look like this. You are tasked with answer a query with associated context. You can access, transform, and analyze this context interactively in a REPL environment that can recursively query sub-element, LM, like in the ablation, they remove this, which are strongly encouraged to use as much as possible, will be required iteratively until you provide the final answer, right? And then there's a whole bunch of stuff, right? They're using the same, roughly the same kind of system prompt for both the GPT-5 and then the Qwen 3 coder, but then the Qwen 3, they have to say this, like they have to say this little thing here, which is like, be very careful about using LM query. as it incur high runtime cost, always batch as much information as reasonably possible into each call. Because the thing, like the Qwen tree was always spawning agent, right? For every line or something like that. So they had to stop it and just restrain it a bit for doing this. GPT-5 doesn't do this out of the box, right? Like it will just like use it properly and stuff. But Qwen tree is just, it just doesn't care at all. Which I don't know, which I find it kind of funny. So this is a system prompt. You can actually take a look. It's in the paper. And this is the only thing that is guiding the LLM, right? So like technically the RLM is this, right? This is the only thing. There's no RL that is being done on this whatsoever. It's literally just a good system prompt with the REPL environment. That's kind of it, right? So this is good. We can then take a look a bit more over here. There's a bunch of patterns that are emerging on the models, right? They're not being told explicitly like what to do, but they end up doing a whole bunch of stuff, right? So the type of thing that they're doing here is that they can probe and then interact with the probe, and then like with like regex or like semantic kind of sub-agent call. They can defer some of the reasoning over its large context by creating recursive LM calls, right? So they're gonna do a function here, and then they're gonna like recursively ask a bunch of questions. Everything in code also here, right? And then create the prompt and then shove it there. And then here you can stitch recursive LM output to form longer composite output, which is pretty interesting. I really like the way it's it's set up. It's very natural. It feels a bit like it's discovering what it can do and what it cannot do. So a bunch of stuff that pattern that they see is that filtering input using code execution based on model prior. So here LM ability to filter input context without explicitly saying it. So they don't know what's in the prompt, but they kind of filter whatever they need to filter based on like their prior information and prior ideas about like what should be in there. It doesn't need to load a lot in order to filter and get what it needs, right? Stuff like just doing regex on like a bunch of information that should technically be there, right? Or asking, you see here what they did, like find all items that are listed that belong to people. It's doing a lot of inferring what should be in this stuff, and then actually going over there and then doing it, or like having another model doing it. They're doing a lot of chunking, like we saw over there. Like they're like splitting this into chapters and then asking it to go and fetch information in the chapter. They are doing a lot of verification. This part is the part that I find funny, right? Like I don't know, like sometimes they just panic and then they verify. There is a failure case that is super funny with, I think, Qwen tree. They just verify forever, and then they got the right answer, and then they just discard everything that they did, and they say the wrong answer. It can verify its information through sub LM calls, and it can pass recursive LM output through variable for long output tasks. So like it kind of is a way to kind of safeguard its context, because it's gonna, like, if you see here, right, like over there, right, this output might be gigantic. You don't know, right? Maybe it's like, I don't know, 20k, but it actually is just this for it. It literally is a one variable, right? And it's using these variables and stitching them together. It doesn't have to see it. You can just trust that like it's good, or you can maybe verify a bit, whatever it is. But that's very interesting. Or you can actually just like look at the length of this and decide if it's a good idea to like open it up and load it into its context. So the variable encapsulation is a very interesting element of how it can safeguard its context. So it's always kind of operating in like a better section of the context than like just raw LLM calls. the baseline that are used, we have the RLM with the REPL, and then we have the RLM with no subcall, right? So like in the no subcall section, all of this is just gone, right? You just don't do that, and you just do it there, and already it is better in some cases. We have also like they benchmark it against a summary agent, which is another kind of methodology that you can have, which is basically like literally like you have summarization happening. There's different ways of doing it, right? But it always is like whatever happened in the past is now summarized in like a smaller format, and then like you take that and then you add the other piece of context, and then you keep on going. And then once it's too big, you compress it, and then you keep on doing it. A bit like what's happening with like Claude and stuff, right? Kind of compaction type of methodology. The issue with this is that if the information is very sensitive, right, in terms of like its actual format, it can kind of get lost semantically after too many compaction. So it's like lossy long context in this specific case. So they're doing a mix of this, right? And what they're actually doing is this over here. In an iterative fashion, the agent is giving input until its context is full, at which point it's created to summarize all relevant information and continue, right? So that's what's happening. And then they're using like a smaller agent for summarization there. Last one that they're benchmarking is CodeAct, which is kind of the React type of framework where I always forget like what React stands for. Like you see, think action, environment, take action, and then response, right? That's sort of like back and forth, right? But in this case, it's like you think, and then the action is code, right? And then you shove this into the environment, and then you have a response, right? So, or you can do that multiple times. So it's kind of similar to whatever is happening with the RLM, but within the kind of the React framework for agents. So the element is using code as the action instead of like doing a bunch of tool calls and just doing like JSON in, JSON out. So that's that. The main result is what we saw here, right? It's working. So this is good. It's actually, it is working. So it's fantastic to see. The pricing is not too crazy stuff. It depends also, like it's highly variable, right? So it depends on like some calls are massively more expensive than others. In like the 50 to 75th percentile, it's pretty similar all across. But then the prices start to explode with GPT-5 here on the 95th percentile. You see here the CodeAct and the summary agent, they are getting massive amount of multiplier. While the RLM is like a kind of double this one, but it's still not not crazy high, right? It's much cheaper than these ones, and it has less biases about like what they actually can be doing. Qwen, same thing, but Qwen seems to be more pricey, right? And remember, Qwen is the one that it has tendency to just go ahead and not care too much about the compute cost. If we look at more details here about the exact number, so we have these benchmarks like code QA, browse comp plus Oolong and Oolong pair, right? And like the task length roughly, right? You see here browse comp, it can go up to like 11 million. It's kind of wild here. But if we look, the base model is not able to do this at all, right? This part is just impossible for it. Like it's too big of context to ingest. So you need to have an RNS to do something. So if you put like the CodeAct RNS or the summary RNS, right, it can get better. So you have 12% here and 30%, 8% here. It's doing better in the code QA generally. And these ones, the Oolong pair, it's like quadratic, so it's a bit more difficult. It's doing not too bad in the Oolong, right? But the RLM, just the RLM, right? The RLM with no subcall with Qwen 3, actually doing better over here on these two benchmark. And then it's still doing really fine here, right? Just with no subcall at all. So it just one LLM in a harness with the REPL, a bit similar to CodeAct than anything else. When you give it the sub agent, funny enough, this one code QA, the performance drops a bit. But here the performance increase for this one and this one, and this one is fairly similar over there, right? So oolong and oolong pair are more like semantically kind of relevant. This is more exact type of stuff, right? Kind of makes sense, right? That like no subcall is better. So this kind of means that some model have some more trouble deciding when to use what, right? For which type of cases. Anyway, and then GPT-5 just generally much more strong than Qwen, except with the no subcall here. But generally, like the performance is better all across, and with the subcall. So it seems to be better at like deciding when to use its stuff. That's kind of it. And I think they did an experiment where they scale the number of documents, right? So here you have 100, you have 10,000 document in context. And in this experiment in the appendix, you see like look what happened in the degradation, right? Because remember the comp plus, the models are not able to do it. Like these ones, the base model, are just not able to do that one. But like if you just increase the number of documents, you can see that degradation, let's say of GPT-5, is just nosedive straight up, right? With 10 documents, it's good. With 50, barely, and 100 is just like almost inexistent, right? Well, the RLM is kind of doing okay all across, and even better when he has all the information over here for some reason. I'm not sure what. And without a crazy cost, here you see the React is kind of much higher at the 1,000, but the RLM is still relatively cheap. So RLM are able to scale well without performance degradation, and the inference cost is scaling not too bad. There's a bunch of trajectory that they put in the paper which are pretty cool, right? You have this one with GPT-5, which is like a happy path, right? You have 1,000 document over there, and then like you can literally see what the model is doing in code, because this is how it interacts with like the environment. And so it's searching for a specific keyword, and it's like looking at very specific steps. You see here the window, and it's trying to find snippet that makes sense. And this is, I don't know, the keyword that it's looking for, right? So it created the keywords and it's looking for them. And then running the regex query, you have like the response, right? And I think this one is making sub LM call to find the answer, which is like this is like what it's asking from one of the DLM. So the root node is asking this for a sub agent, which is extract the following from this article. What festival and town is this about, and what year was this specific celebration held, blah blah. And it will respond all of this, and then based on this it will check the information, right? This is what is gonna have, and then it will be able to figure out that like, yeah, this is the response, it's Maria Dalmacio, and then this is what you will output at the end, right? Print winner first last, and then first last. This is what he has. So it's cool. Like none of this is kind of hard coded or tooled. They just go and do Python. Over here. Is this the one, the funny one? This is the funny one. We're gonna take a look at this one, right? This is the last one, right? So this one costs $1. This is the question, and it's on the oolong pair, so it's kind of difficult. It's like you have to like double check and verify a whole bunch of stuff. And then it says that the model will begin by probing the context with various code snippets, right? It's probing its stuff. And then like it decides to check semantically, like classify the data using a sub agent call. And then it goes, right? And it processes this in batch, and you see it's like doing this in what's it, like it created this function which is doing the LM query. And it's like continuously like calling this function, right? And then like the recursive LM calls will do their stuff. And then the root LM will look, right? If the whatever instance satisfy the query in this case, and then has the pair, and it has like the information, right? And then it will look at it, and what it will do here, it will continuously verify its answer. This is Qwen 3 coder, right? I think in this case, so it will repeat this process over there, right? And attempt again to regenerate the answer, and will do that 5 times like over and over again, and I return the same answer. And when it asks to be like actually like give a final answer because it's starting to run out of context, yeah, it's just gonna be the root LM generating an answer out of nowhere and then just like spitting it out, which is gonna be the wrong answer. So I don't know, like this part I found it absolutely I don't know, like, it tells you a lot, right? Like the Qwen 3 coder will do that. The GPT-5 seems to be doing this a bit less, like this kind of neurotic double checking. But just the fact that it doesn't trust this stuff that it's being produced by like itself, technically, like these sub agent, and then just verifying again and again, it tells you a lot about like the benchmark, the difficulty of it, but also like what the LMs are actually doing when they get to difficult stuff like that, right? So I think there's maybe stuff that can happen in order to make the model and steer the model in like being more sure about what it is looking at. But it really looked like, I don't know, like a student which has like 1,000 document open and just double checking and then just like not trusting itself. Yeah, this one was funny. There's other ones, but you can read the paper. It's all there, right? And it gives you a sense of what's going on. And I really like that in the paper where like the quantitative information is fine, right? It's all good, but I really like to see the exact qualitative vibe of how these things are running. It can, by the way, you can also try to run it on your own, right? It's just literally a harness that you put around it. And the last part that I really liked is this one is negative result. Honestly, I think like all papers should have that. Like just tell it, like you found something cool, perfect. Just tell us what didn't work so that we don't try to do it again. So using the exact same RLM system prompt across all models could be problematic. So like this is the Qwen 3 thing. They had to make this change. Otherwise, like Qwen 3 was just like spending like crazy. This part is interesting. So model without sufficient coding capability struggle as RLM. So the corollary, the opposite is also seems to be true. Like models that are good at coding seems to be good at long context because they can manipulate the REPL environment efficiently. Yeah, thinking model without sufficient output token struggle as RLM. That's also an interesting one. So they tested a whole bunch. You can check out like this other blog post from Permitellect, Recursive Language Model, the Paradigm of 2026 by Sébastien Maman. He tried a whole bunch of other LLMs also. So you can have a good kind of overview of what's going on. RLM without asynchronous LM calls are slow, right? Like in this case, like the calls are blocking. So like you're doing stuff step by step. Maybe like doing it asynchronously will help. But then you get into the weird setup of like what happened. How do you continue if like stuff is not done yet with another sub-agent, which is an interesting problem, I think. And depending on the model, distinguish between the final answer and a thought is brittle for RLM, which is also super interesting. And maybe like it tells us a lot about like these failure cases, right? Because it couldn't recognize maybe that it has the final answer for real this time. So like it should just like go and commit. And it's still think that it's maybe a thought and it just needs to kind of get the final answer again and again. I don't know, it's really grad student coded, this whole interaction, which is a bit fun. There's a bunch of limitation here that you can read in order like what the stuff hold, but we're gonna actually ask Alex a whole bunch of questions. Thank you for coming and answering question for all of us. I think it's really cool. I really like the paper. Well written, also like it remind me of the TRM actually paper. Like yes. Very, I don't know, like a very not simple in the sense that like it's nothing impressive, but simple in the sense that it was easy to follow. So we like that. To start off, can you tell us a bit about yourself and like just your background and like research interest for everybody here?
100%, yeah. And yeah, I will preface by saying hopefully the paper was easy to follow. I think actually some of the earlier iterations of the paper we had I had wanted, or I wanted to write in some like theory related motivation for like why there was actually a whole thing about like why certain problems are harder than others, which I will actually talk about today, but I scrapped in the paper mainly because I think we didn't have enough like strong evidence to support that like what I was claiming was actually true. But I think intuitively you can see a lot of it. But anyways, so for context, I am a first year PhD student at MIT. I think it is very funny when people say I'm an MIT researcher. I've only been there for like 3 months. But I graduated from my undergrad at Princeton back in 2024. I originally wanted to do math, funnily enough, and I guess like it's what the school is known for. But I did a bunch of like really random stuff. So like I did some like exploration with a friend into like blockchain schemes and then all this random stuff. I did a bunch of like more core RL work earlier on in my undergrad, and then eventually near the end, I started working with the SweBench team on like SweBench related stuff, mainly SweBench multimodal, which came out last year, and then I got really involved in GPU mode, which is also really random. So I was really interested in GPU programming. I currently help host all the competitions, which is not at all related to RLMs. But the point I'm trying to make is that like I think a lot of my current research interests and ideas are kind of motivated by lots of random things that I've done in the past. And I think the field moves super fast. So there isn't really like one thing to be like fixated or focused on. But yeah, currently I think RLMs are my main research focus. And it's not necessarily long context problems, which I will also kind of elaborate on as we go. But I think that like in general, for this year, there's a lot of really, really interesting research that we can do for language models that isn't necessarily like systems work or like infra work. But yeah.
Cool. Yeah, it's really cool. And I see that you've done a whole bunch of benchmarking.
Yes. Yes.
That's very interesting. Can you tell us a bit about like what motivated that work also?
So I will say, I think, like, I'm not going to lie and say, like, I love making benchmarks. I don't think making benchmarks is fun. Everyone wants to do the flashy thing, right? Like, you want to train a 100B model and then do all this cool stuff. And so for context too, the benchmarks that Yassine is referring to is, well, SweBench multimodal was the first one with the SweBench team. And then kernel bench, which is like, LLM generated GPU kernels and evaluating those. And then the most recent one is this thing called video game bench, which is like trying to evaluate vision language models that can play an assortment of games. So these are like games from the 90s, like Doom, Mario, Kirby, like these kinds of things. But I think that this, you actually talked about it earlier, but like this RLM work, I think kind of highlights too that like we don't have a lot of good benchmarks. And I think when like the reason I ended up working on benchmarks every single time was because I wanted to work on a particular problem, but there was just no eval for it. And I think like this actually is a really big problem in the field in general. I think I have strong opinions on like what evals should look like. I think that like we kind of have a problem of like evals currently are not, a great indicator of how good a model actually is, even on the task that you're evaling. So like, for example, there's a lot of evals for math and coding, but they're not even great evals for like whether or not a model is good at math or coding. So this is something that, I think, needs to change. And I don't think a lot of people like working on evals. Like I'm gonna be honest, I don't think it's fun, but I think it's really important work. And Unfortunately, I might have to come up with evals for RLMs and future works like this, but we'll see.
Yeah.
Yeah.
I think generally long context, because long context is worse because like, yeah, really have to think hard, right?
Yes.
And then like there's a lot of document then, like what you gonna do? You're gonna verify each one? Like no, man. And so you have to kind of make it RNS and then do it properly. I mean, actually like the people that have a lot of long context stuff that are relevant for LM are actually like the closed lab, which
Yes.
they have no. Why would they publish their internal data, right? So that's kind of a bit of the problem, and I realized that when I was reading the Minimax paper, text 01,
Yes.
text 01, because they were talking about like this translation long context task where there's this dead language, only 100 people talk it, and then like there's like this book that you give in context, and then you check if they can do the translation, right? In paper makes a lot of sense, but then like what happened is like at some point even the models, the newer model are getting good at the language even without the book, because they're seeing the book at some point. So like then it's even harder to come up with like good long stuff. So you don't really know if the model is actually able to process the longer input.
Yeah.
So when you actually give it to your stuff, it just suck. And then you're
Yes.
like, why does it suck? It doesn't have the stuff in context. It never seen that big of an input. And then that's kind of the end of the story. There's nothing they can do with it. Which is actually what interested me a lot with this paper is like, instead of trying to like bring in context all this information, right, and try to come up with like massive amount of training data for long context, well, they can have a small context. It's all fine, but they get like the tool that they need in order to kind of mine, like literally data mine the information. A bit like a PhD or like a graduate student. Like they don't have everything in context. They have the data sitting there. They have their Jupyter notebook. And then it just go, right? And then they learn about, and at the end of a session of a notebook, they get some insight, right, out of it. Maybe it's wrong, but they get some insight out of it, and then they can move with it.
Yeah. Also, funny story. So in the paper, there's only 4 benchmarks, and even for like the code QA, I think you mentioned it. It's part of a larger benchmark, long bench v2, which I think arguably is maybe the current most difficult long context benchmark. But the reason, so we actually evaluated on a lot of benchmarks, like a lot more than is shown in the paper. And the problem with a lot of these benchmarks that we ended up finding was like either A, the RLM can just solve it basically. But like we don't report this because the way that it solves it is by using the code environment, which is like not like it doesn't need to use the sub LM calls. And like it's kind of a silly thing. So like one of the examples is like another benchmark or another task in that benchmark is like computing a long math sequence, like a long arithmetic sequence. But like if you plug this into Python, like of course you can just do it. Like there's no, it's not a hard problem. But like you'll get like GPT-5 can't do it. Like it can't get everything correct. And so like the scores you report are like, oh, the RLM gets 100%, but GPT-5 gets 0%. But it's like, that's not really an interesting result because like, well, of course, right? Like, and the other problem is like, oh, the base model can just do it. Like it can actually just solve the task. And like one of the issues we ran into that was like really silly, was we had examples where like the task would be about like a book or something. And you like take the book away. Like I tested this. You just remove the book, and the model can still solve the task. So like it doesn't need to read the book because it knows what's already in there. So this is like it's really really hard to find good evals. And I think like for anyone that's interested in doing research or something right now, this is an open problem. Like it's genuinely like a low hanging fruit of like you just need to find a good eval that's like realistic and like that people that you want to see models actually solve.
Yeah, I think that last part is important. Like that you actually want the model to be able to solve, because toy problems are cool, but I mean, if you want to bridge like when you can actually bring the model to your whatever that you're building, being already knowing that it can solve like a related task is already something. Okay, I think we got a bit through the high level overview. Can you talk to me a bit like about the intuition that led to like this? Because you could have went, if you look at the related work, you could have went all sorts of different ways, but you decided on REPL environment. What triggered this?
Yeah, so this is actually a really important question. I think there's like I don't want to say that like I'm a genius, like this is a completely new idea, like no one's ever thought of this, which I have seen online, like there's a lot of like, oh, like doesn't Claude Code do this, doesn't like XYZ method do this, or like aren't doesn't OpenAI already do this in Codex, and I think to some extent yes, like I think so the way that this idea kind of came about was basically like nowadays I think models are really, really good. And I want to preface by saying this because I think this is a very timely idea. So if you tried to do this like maybe last year, so like we've tried this with DeepSeek R1, for example, it's actually not very good at doing this whole thing. And like I think a lot of the fundamental model architecture / training research was really, really important to lead up to this point. So I think the best way to think about this is like methods like Claude Code and Codex that do this kind of like very smart code-based management thing, where instead of feeding the code base to a model, they use like special tools. I actually would say this started with like SWE-agent and OpenHands last year. But like this idea of not feeding in all of the information directly to the model and using specialized tools to like navigate this information, this idea was like very exclusive to code or like even like software engineering tasks. And I think like the intuition came from like, oh, like, a programmer is not going to read the whole code base at once. And I think like the core intuition behind this idea is like, well, you can actually do this for any task. And actually, like Claude Code and all these scaffolds, like they are highly like specific to code. Like you can use them for other tasks, but the models themselves are like post-trained specifically to solve coding tasks. But I think like the nuance here is like, yes, RLMs, like the idea is really good. It can do long context things. And this is really important. Like you can slot it in, like you can slot in an existing model and show that it works. Like I think for the purposes of the paper, this was the most important experiment we wanted to show. But I think actually like the more subtle thing here and like why I'm excited beyond this initial paper is like the implication is that you can actually start post-training models to do this kind of paradigm. And this is a lot cheaper than trying to extend the context window of a model or like build a larger model. And I think like we are starting to enter like an era where these models are actually really good. Like these transformer-based neural networks are really, really powerful. But there almost is like very little need. Like I want to be careful with my words here because like, we should continue to improve models. But it's like exponentially more expensive to, even like double the context window of a model. And like, I think the point that I'm trying to make here is like, they are already so powerful for, transforming text of a certain context window size to text of a certain context window size. But you can actually like chain these things together and you can produce a significantly more interesting system by doing this without, incurring really, really expensive scaling costs. So in my mind, like this is another axis of scale that is like very interesting. Now, we don't talk about this a lot in the paper because as a paper, we can't claim things that we can't prove. But I think like this is like a really important point. I think this is actually why, for example, like Prime Intellect is really interested in this approach. It's not necessarily just for the long context part. I think there is like a piece of it that's like really, really important, which is maybe all future models are actually interacting with your context in this way. So, yeah.
Yeah, for me, what sparked my attention here is that it has a similar shape in terms of just the thinking and then a chain of thought kind of trick, right? Because it's simple enough, it works all across the board, but then you can actually RL it so that it's even better, right? And we haven't done this yet, but I think it will have it has the same characteristic as this setup. And the other thing that I think is yes, coding is economically super important. I think for just the whole field, because if it starts to work even better on bigger code base with just a simple framework and everybody can do it, then there's going to be more tools that will be able to work on bigger code bases, and then you get into enterprise and the money is there, right?
Exactly.
This I understand, but in my view, it unlocked the whole scientific research agent type stuff that is able to go for longer amount of time.
Mm-hmm.
And is digging into this, because fundamentally this is a grad student.
Exactly, yes.
That's the feeling I had, is hey, I have this big task and it's complicated, it's super long, there's a lot of this stuff that I need to take a look at, but that's it. So I'm gonna parse through it a bit, figure out hey, this is relevant, this is less, and I'm gonna give it a task for next week. My task for next week is try to figure this chunk, and then you go and you figure this chunk, and then you get it out, right? And then you work on it, and then but this flow, and then literally it's in almost a notebook, right? Jupyter notebook. This flow leads to some amount of facts or information being found that then can be used to answer a bigger question, right?
Yeah.
This I really liked. I found that it has these setup. The other stuff that I really like, and I want to check with you, was this on purpose or not, is that it's very minimalistic. There's no massive harness of any very bell whistle. It's a system prompt and then a REPL. Was this done on purpose, or did you try a whole bunch of stuff before getting to that?
Yeah, so this was intentional, but we also tried a lot of stuff before that. So I think what we ended up settling on was I don't love calling this a scaffold, because it is I want to be clear, it totally is a scaffold, but I think scaffold makes it sound like this is a type of a new type of agent that we're building that we want you to use. I think more fundamentally what this is a very particular way to do model inference. And keeping it as minimalistic as possible is very important for this, because you can't afford to train a model just to be used as an agent, unless you're Anthropic and your goal is to sell Claude code. I think if we're more interested in general model capabilities, we want something as thin as possible on top of the model. And I think that was kind of the guiding principle for how we designed this.
That makes a whole bunch of sense. Wait, there's a question here.
Yeah.
Just wondering, are there a problem where the context expand instead of contracting at the meta, which you might want to all the LM connects can't fit in?
There was a similar question earlier about what if the context window of one of the models fills up, one of the intermediate models. Yeah, I mean, this is definitely a concern. I think in the long term, the hope here is that, or one of the core ideas of an RLM is that no single model call should ever exceed a certain length. This is kind of this is the hope, right? Now, how you actually guarantee this is not super easy. I think what we found in our experiments is that if we just let this thing run as is, it actually just never fills up. It never even gets close to filling up. But you can imagine if you go to a harder and harder task, maybe it does fill up. I think ultimately what this should look like in its full form is a recursive language model will be spawning another recursive language model. And in this sense, the actual intermediate like model calls will never exceed a certain length. You also could implement like tricks like compaction and stuff that like Claude Code currently do. I don't love this because I think it kind of takes away from the core idea, which is that like this entire process should be a quote unquote like no information loss process. And what I mean by that is like at no point, like the reason why we store everything in the REPL is the model should technically, like in theory, have access to all information, like in its purest form, not in a compressed way. And you kind of want to maintain that like throughout the trajectory of the model as well. But yeah, I think like the short answer is like we haven't run into this issue in like the current experiments we run, but this is totally like a plausible issue. And I think like it does get solved by like deeper and deeper recursion, because like the idea is you keep splitting up the context. But I think like we don't have a strong like robust guarantee here. But like maybe that's a future work kind of thing as well.
And like in my view, like compaction is kind of interesting in the sense that like if like you're working toward the specific goal and then the compaction kind of makes sense, right? Mm-hmm. But like I come back to this grad student type of workflow. Imagine if like the grad student was cleaning the data, right, in a specific way and then throwing the raw data, right? Like it will be kicked out of the lab ASAP, right? Yeah. You do this and then you messed up, I don't know, the filtering or whatever it is. Well, congratulations, right? Like, what the heck are we gonna do now, right?
Yeah.
And I think this is because like I always come back to the scientific discovery type of shape, because I think this has a high potential in this realm, because like you have the thing in the raw form, mm-hmm. and then you're digging through it, right? And I think also what the Pataki is hinting toward is that like there's these experiments now where like for scientific discovery where the model is running for like days and whatever it is, right? At some point, like it's creating a lot of context, because like let's say the REPL is just like it's just like literally 100 meter long in terms of a back and forth. At some theoretical point, it should fill up the whole context, even if the output should be like one answer, a name, whatever it is. Yeah. But I think like having the raw data, having the thing digging through it, is already like a big piece of the puzzle of like being able to generate like insight and facts out of it. I have literally a dumb proposition here, which like amounts to like literally jamming a MySQL database in there and then storing a bunch of facts. I mean, you already have REPL in there. Like, why not adding a MySQL instance and storing a bunch of stuff? But we're gonna get to this. Before we dive into that, I just want to get your raw thought here about like long context in the model, right? I've done a video on this, and I've been digging through this. It's just like literally a hard problem, because you always get into like this kind of trade-off, right? And to make it good, let's say you linearize the attention or whatever the heck, you do block stuff, you do lightning attention, you do all sort of weird like wacky thing, and then you optimize GPUs in order to make it work so that it's actually faster, right? Like, do you think there's something there to juice up still, or like it's just the wrong way of thinking about like the long context problem?
Yeah. So I think it is the wrong way to think about it, and I'll explain why. So I think scaling like the context window of a language model has two main challenges. The first one is the systems challenge, the systems level challenge, right? Like, attention is actually not even the issue usually. But like, let's say like, attention is quadratic. Maybe you can use linear attention, sliding window, stuff like this. Like, and maybe you need more GPUs to train a larger model, et cetera, et cetera. Like, maybe you're 10xing the cost of your training run. This is definitely a challenge. And I think like, my take is that if this was the only challenge, we would be able to continue improving the models significantly. Like we would be able to extend the context window beyond, like much further beyond what we currently have. This I believe, and I think if you ask anyone in like the systems community, I think they would likely agree. I think maybe not. Maybe there's some like really strange reason why you can't do this, but in its current form, like just scaling compute and scaling model size is not like, it is just purely a cost issue. Like I don't think we've hit that wall yet. I think actually the more subtle issue is the data, and this is a core reason why I think RLMs are so cool, because I think that we often take for granted that the way that we've trained language models is effectively using like the internet or using naturally occurring language and kind of learning this distribution. But this like naturally occurring language distribution is not like unbounded in length. Like I think the sequences that we observe like in the wild tend to be like distributed according to some like mean length and variance, right? And I think like we have gotten away with the fact that like language models continue to improve because we have these like naturally occurring sequences that capture the distribution that we want. I think the way that we have done longer and longer context things is we have to generate synthetic sequences, like synthetically long sequences, and train on these sequences. The problem though is that like it's not fully convincing to me that like doing this will like net you any longer term benefit. And I think the greatest example of this is the like practical failure of reasoning. So like reasoning models are really good, right? Like don't get me wrong, they're amazing. It was like a great breakthrough of the past year. But there's like a lot of papers that have come out recently that basically show, or like experimentally, that reasoning is this really silly thing, because the actual content of the reasoning trace is like almost irrelevant to the final answer. And like part of the reason that this is happening is like at that scale, like at this like sequence, like I think the way to think about this is like as you get longer and longer sequences, you need exponentially more data to like fit a proper distribution, right? Like there's like an entropy argument here. And I think what's going on is like with these reasoning, like these long reasoning chains, what we've kind of observed is like, well, the good part of a long reasoning chain is that it conditions your model well to get like the right output. Like you can think of it as like a way to pick out the correct outputs from like what you actually want. And reasoning, we've kind of seen as like a way to do this, but what ends up happening is like, with the Quen experiment, we saw this with the RLVR stuff, like, oh, you can actually just post-train on random stuff and like you can still get like some good answer. Like, this is a really odd thing. But the beauty of like the RLM part is like we can actually keep the language model input and output distribution within a length that is actually naturally occurring. This is it's a weird thing to like wrap your head around. But I think like this is the whole context rot thing we've been observing, where like you make the sequence like really long, and all of a sudden the model performance like just tanks, and it's like why? And part of the reason is like I think we shouldn't I don't love thinking of models like in an anthropomorphized way. So like a human obviously would not make these kinds of mistakes, but I also think that like a human learns in a very different way. And so like we should think of these models like, yes, they're very impressive, they generalize well, all these things, but at the end of the day, like we do have to think in a very mathematically principled way of like how were these trained and like what are they doing? And I think if you think this way, like it's very obvious that long, like just the transformer model and training it on long, like huge context sequences is a really like difficult thing to do. And I think like with RLMs, the idea is like we actually don't have to do this. We can do long context things without training them in a long context way. And there's a lot of benefits, I think, for doing this. But yeah, that's my take.
Yeah, no, I agree here. And My other view of long context, like if you want to kind of go and play around in the internal of attention or like how everything is set up, the issue also is that theoretically it's better and it's faster.
Yes.
But practically, when you look at the practice, like flash attention v whatever is much better in all metric because it's optimized for the GPUs.
Yeah.
So then you get like these theoretically fantastic like advancement that are absolutely dinky and worthless in practice, and then nobody is gonna like do the work of making the GPU stuff that you need in order to use them efficiently.
Yes.
So then it's like, why did we even do this stuff?
Yeah.
And I think that if there is a method that can sidestep this, like for sure we're not going to go forward into the
100%.
long context. Like the slice of what they see is enough. And also reasoning for me is just like I see it in two ways, right? The first way I seeing it is like it just helped the model like filter out like, I don't know, like wrong kind of answers and then just like bias it toward where the answer should be, because technically you could just inference scale at first shot it and then it will output maybe in this mess the right answer, and if you were able to pluck it out you would be able to do it. But you could do it like either way. But also if you look at it from like an activation like perspective, right, you get kind of these trace of like activation that are happening in the model, because the model doesn't have a state. So you have this activation, and then this activation will be with another input will be able to give you this other activation, and then at some point it get the right shape in order to do the right activation for the stuff. So like reasoning is nice, but the fact that it's outside is a bit kind of weird, and like as it goes it just is like using like the useful context inside. Wait, there's a bunch of questions. There's somebody that says you mentioned Cloud Code and other agent already do intelligent context retrieval management to some extent, and the exciting part is perhaps more on the post training. So this is a question about like is the interesting part of the RLM the RL that we can do on it? What's your take on that?
Yeah, so I want to be careful here because I think like well, I'm getting used to this too as a new PhD student of what I can claim and what I cannot claim. I think the interesting part of the RLM paper is still probably the main result, which is that like, hey, like, you know, first of all, like one of the things that we wanted to solidify in this paper, which I wanted to do in math, but I think maybe the best way to do it is just in plain English. Long context tasks are not equal. I think this is one thing, like, I don't know why this wasn't made clear in the past, but like, obviously needle in the haystack is a very easy thing to do. But like, if you were given a really dense, like, long context, it's really hard to process this thing. And the main contribution is like, even without training, like even with no training, you can do this really, really simple, like task agnostic method. And you can take current models and you can scale their performance on really, really long sequences. And it can actually process these really dense and also really sparse inputs very well. I think like this is the, you know, we have the results, and I think this is like, as on its own, like this is already a really cool result. Like I think if there was no RL, like no future thinking thing, this is a cool paper. Like I'm very happy to publish something like this. I think the RL part though, or like the training part, is more like, why do I think this paper is more interesting, like beyond this, like for this year, right? So like why is my research still focused on RLMs even after I've come out with this paper and probably we'll try to publish it somewhere? And I think that's where like all this other speculation and all these things come. And like, I think a lot of it is grounded in intuition. Like I think a lot of people are also seeing that this is a really interesting bet to make, similar to like chain of thought and some of the other things that have worked in the past. But yeah.
Yeah, and it might, like this paper also remind me of like I think it's the meta paper where they jam like a coding environment into the world model of the, thing, and it got better and stuff. I just want to show this. I knew that the discourse of I still want to dunk on anybody that is working on at Meta, right? But like this, like at this point when I saw Llama 4 Scout, like this whole block of needle in a haystack to 10 million token, I knew this was absolutely worthless. Like it's not the thing. Like it's not just like a needle in a haystack problem. It's much more complicated than that. And like I think you put it well, and I would have liked like that, like this theory was pushed a bit even further about like this kind of angle between the the size of the context and the difficulty of the task. I think this is something that generally in the discourse is not well explained. And I think like the other part is also like I don't know, like the average capacity, like the average useful window size of the model. Like if we have these three kind of axes, then it's a bit easier to say, like roughly speaking, for this specific task, how hard it will be for this specific model to be able to interact with it. Okay, cool. I had a question about, we can maybe dive a bit more into the RLM structure, because I think there's a whole bunch of questions about it. So my first question is that you choose REPL for this, right? Which I think makes a lot of sense. But you did ablation on the sub-agent, right? So you remove the sub-agent. Do you think you can do the ablation on the other way around, where there is no REPL and it's just like a whole bunch of sub-agent that are just working on the context without having it fully loaded? I think this part I think was maybe missing, in the sense that like you don't have to load the full thing and then they just go and do their stuff. It's just like it's still an environment variable somewhere, but they are not writing code. They're just like working on it. Did you think about this, or this is useless when you look at the other?
No. So this is something that we missed, and actually we're running it right now. So there's two new things I'm adding to the paper, which I'm not really going to make a big announcement about. I think it's more for also we're like submitting it to a conference. But one of them is that it's exactly that. We need a baseline that is effectively like, can you take React or Kodak or something and give it sub-agents, but you don't do this like offloading into a REPL kind of thing. And the point of showing this is like, actually for RLMs, like I think another thing I want to be clear on with the RLM thing is the idea of taking a model and giving it access to submodels is not new. We're not the first people to do it. There's a few other works that have tried this. Obviously, Claude Code intrinsically does this. I think there's an argument to be made that like I think the sub-agent way of doing it will get phased out. What I mean by this is like the way they do sub-agents is like you define the sub-agent and then like Claude Code will be smart about using it. I think ultimately, like in the long run, this will just be completely removed and Claude Code will decide what sub-agents it wants to use. But even ignoring that, I think the thing I want to be clear about is like there's two key parts of the RLM. One of them obviously is the recursion part. But the second one is like, how do you actually do the recursion? This is like a non-obvious thing. And I think the REPL is one way to do it. Like I think and there have been some other proposed ways I've seen online, like using a file system, and bash commands. Also great. Like I think the reason we chose the REPL is like was mentioned earlier, like these models are pretty good at coding. And I think like maybe Claude, maybe Opus 4.5 can also do file system management really well. And that's great. And we should definitely try it. Like I think that's one of the things we want to implement in the open source library if people want to like use it. But the REPL, I think, is like the most intuitive way. Like, I think Python is really easy to read. And it's like really easy to like say something in English and write it out in Python. And so, yeah, this baseline is very important. I think we're currently running it. The results are probably likely what you'd expect. But I would say the main thing is like this setup cannot handle long context for obvious reasons, right? Like it still has to ingest the full prompt. But yeah.
Okay, that makes a lot of sense. We have a bunch of questions about sub-agent. Well, my first one is like, does the two ways. Does the model know how many sub-agent it is spawning, and does the sub-agent knows that it's a sub-agent? Or just running on the task?
Yeah, so in the current setup, no, we actually provide as little information as possible. The reason being, like, we want it to be, if it can work without this information, like, that's great, because people can experiment with this if maybe like tune this if they think it'll work better. The model, I mean, the model implicitly knows how many sub-agents it's spawning because the code it generates like should tell it like how many it's spawning. But I think the Quen 3, experiments clearly show, like, well, it maybe doesn't have the greatest grasp of how many, especially if it writes a for loop, right? Like, it writes a for loop over this long
I think this is it. And also, like, I think, like, it might get confused because it also is writing a for loop and encapsulating the LM query inside a function call.
Yep.
So now you have, like, multiple layers of abstraction about what the heck you're doing. Poor dude is confused out of his mind.
Right? Yeah. So I think, like, a lot of these things can get baked in. A lot of these things can also get post-trained out, to be honest. And as for if the subagent knows that it's a subagent, I actually think it shouldn't know. And the reason, like, we did it this way is, like, a big part of, like, the thesis here is you can use an RLM on a single model. Like, so yes, you can use an RLM to spawn, like you can use GPT-5 to spawn Gemini 3. That's fine. Like, that's great. And I think actually that's likely what it will look like for maybe the next few months. But ultimately, I think what we really want is a single model that acts as both a regular model. Like, it should still be a regular model, but it should also be able to be used as an RLM. And when it spawns itself as a subagent, it should treat it like it's a regular call. It should have it shouldn't need the prior that it's a subagent. Like, it's just being asked a question and it has to answer it. So I think, like, this is going to be a key thing, like, moving forward. Like, how do you train an RLM such that it still maintains its performance as a regular model, but it also has the ability to be an RLM? This is like an interesting thing.
Yeah. But, like, I'm saying this because, like, for the Quen 3, like, in order for it to work, what happened is that you had to literally tell it in the system prompt that, like, my guy, just watch out for the compute cost because, like, this is too much, right? But I think, like, it knowing, like, how deep it is right now in subagent call gave it this information without having to tweak the system prompt, right? So you get, like, one clean system prompt that just worked everywhere, and then, like, you're just, like, giving this model information about, like, because implicitly, like, the number of agent that is spawning is correlated with the input cost. It's like 50,000, like 50 agent deep. It should know at this point that, like, it's messing up. And I was reading the Parametric blog, and they gave it hint also on the difficulty. I think this is also another part that is super important because they seems to be kind of poor at assessing, roughly speaking, what is the difficulty of this task, right? And, like, how much this should be used in terms of compute in order to solve these tasks. So, like, that was what prompted this thought. The other thought is that if we want to, like, do kind of, like, recursive sub-agent calls, right? My view is that like, the axis that you were talking about, like, how long the input is, and, like, how hard the thing is, should maybe be something that the model knows about, right? Like, look how much I spent right now, and look at what I'm giving to you. You're, like, I don't know, agent number 52, and you're 3 layer deep right now, but you have an easy task, right? This task is supposed to be easy. So in this specific scenario, the chances that, like, this sub-agent will, like, think about spawning another one's like, no, man, I can just solve it. This is supposed to be easy for my breed of LMs, right? I think, like the part that is hard here is to, like, be able to implicitly know how hard the task is. But I think if you're able to give it should kind of direct the LM normally. Like, you see GPT-5 seems to have a better reasoning about compute costs and just, like, how much things are hard or not, right? Quen 3 seems to have absolutely no idea about that stuff.
That's a great point. I think honestly, this is something that should be experimented with. Like I think what you're saying like could very well be actually the way that it's done in the end. So yeah.
And we have information here. A question that like fit with the one I want to ask is that in the paper you said the system prompt is fixed across all experiment. So the sub agent doesn't even know the system prompt, right?
Yes,
It doesn't know that it's like in RLM type of stuff.
Yep.
Okay, cool. So that's
because we're doing depth equals 1. The sub agents are just models. They're space models, and they're
that
given
need to fix one specific task, and that's it.
Yep.
And it doesn't have access to its ancestor tree. Doesn't know anything about about that stuff. Okay.
In this case, I think it's because the tree is not interesting. I mean, it's just a root and then a bunch of leaves. I think if you start to think about more like higher recursion depths, yes, then I think actually maybe we should start thinking about like telling it where on the tree it is, like what, like maybe give it a little bit more context about its parent node.
I think that's because I go back to the lab analogy, right? Which is like if somebody is getting handed like this project, like, hey, can you do this? And the grad student is like, okay. And then he's gonna take it, look at it and give it to another one like, hey, dude, can you do this? And then just give it like the actual thing as is, without knowing that it's been the sixth guy that has been, and then this stuff. That's one thing. The other thing is that if it knows it's easy, right? It is like arguably easy. The chances that it will go and then actually do it are a bit higher. I've pulled out a bunch of neuro-inspired research here on that. Like it do change the behavior of human when you know the difficulty of the task. If you know it ahead of time, right, the chances that you're gonna do great on the exam is really high.
Yep.
If you know it straight when you have to do it and you had no time for preparation or whatever it is, then it's different, and depends on if you're anxious type or not anxious. In this case, I think Quen 3 is anxious and GPT is like pretty chill. But like it has an organic human type of intelligence and impact, and I also found some paper that show that like it also has an impact on LM's ability. It is just not that great to assess like the complexity of the task.
This is interesting. The last thing I'll say is like I think this is for the more theoretically inclined people. This is a really interesting problem actually of like local and global observations. So if like I don't know how related this is to like POM DPs like in RL, but in general, like what we're dealing with here is like this system where not every model or like not every actor in this system has all information about what's going on, which is important, right? Because I think the thesis here is that it can't. But there is sort of maybe some things to be said about how much information should you give each of the models at every layer. Like there is likely a way to like characterize this very well. But anyways, not that important.
Yeah, but no, I think it's actually super duper important, especially like if we're thinking about asynchronous versus synchronous.
Yes.
Like in the asynchronous case, I think it doesn't matter too much because you just go and then it just do its stuff and that's it.
Yep.
But in the synchronous case, I think there is a chunk that is missing, which is where we store all of the context or the facts or like whatever it is like that we're like directly mining right now. And then this is being used to kind of double check facts or like in some shape or form kind of align like the rest of the model behavior. Okay, I had a question about the hardness question. I think we touched already upon it. What's your like raw intuition here about like why Quen 3 coder is like making so many calls like a sub agent? Like I think I've said a whole bunch of stuff, but like roughly speaking, because it's still big, it's like a 400 something B model. What's your take here?
I don't have a fully like principled way to answer this, but I think like we have seen that some of these models, like Quen 3 especially, is like heavily benchmark maxing post-trained model. And I think like as much as, we like to make fun of OpenAI and all these companies, like I think ChatGPT or like GPT-5 and Claude and these models or like Gemini tend to be, I think pretty good at like even newer tasks that it hasn't really seen before. They tend to make just more principled decisions. I think Qwen 3 Coder is just a case of like, it just isn't like, it's not explicitly trained to do this kind of thing, and so it makes very poor decisions. That's my speculation. I don't know. It also could do with the task that it has been trained on in the past, and like maybe it's used to just spanning. I don't know, but
right.
Yeah.
Because like I think this is pretty important, because if they're kind of like fried up with RL, and we need to RL some more, right? Like this may need to be happening a bit earlier on in the post training of the model, if we need to RL the model on the RLM. Also, just rough intuition here. Like, what do you think? All of the model are repeatedly verifying their information, because like this is something else. Like spelling sub agent is one thing, but then you have the answers, but you're verifying it again and again.
Yeah.
Right? Like, why this is, you think?
Yeah, so I think, based on my experience using even like coding IDEs, I think a lot of models, or I think trajectories are a very unnatural form of text. Like, if you think about like a trajectory is like a concatenated sequence of input outputs from a model, which these haven't really occurred until recently. Like this wasn't like a natural thing that you would really find on the internet, for example. And like one of the things that is like kind of frustrating, like I don't know, I still don't like fully know a way around this other than maybe post training, is when these models if the model, the one thing I've observed is like if the model comes up with the answer really quickly and the trajectory is really small, the model tends to just finish it right there. Like it tends to just be like, I'm done. Like there's nothing here. And I think again, I don't want to like anthropomorphize this argument, because I don't think the argument I'm making is not that as the sequence gets longer, the model is more like uncertain or something. I think what it really boils down to is like when the sequence is really long, the models make suboptimal decisions. Like they just don't like, they're just not very good in this setting. I think we've seen this in the past with like the jokes we've made with Cursor. Like when you have a really long history, it just starts to make really odd decisions. And I think this is like a similar thing here, where like basically what is happening is for whatever reason, like the high probability actions it should take is just to like retry what it just did and verify that it's correct, and it gets stuck in this loop. I think Qwen 3 is the biggest offender of this, but this is like a known issue with Qwen 3, right? Like it tends to repeat things. But it actually does happen with GPT-5 as well. And I think like this actually goes back to the issue before about like training long context things. Like I think even at this smaller context window, like maybe like 100K or like 50K, it still makes these really silly decisions. Like I would say it's probably a training issue.
Yeah. In my mind also, it might have to do with like the fact that these are stateless. Yes. And like you said, like it's not it's not moving them enough out of the distribution of like, I'm gonna have to retry this again, right? But for us that have states, what we're seeing is that you dumb like piece of trash, it's been 4 times already. Like it's enough. Like it most likely is good, but it's not enough. It's like, no, this is still uncertain. But like the fact that you're trying it 4 times should make you more certain that like this thing is most likely okay. Which bring it back to my idea of like this kind of fact type database, right? Like you generated this fact, and two other subagents generated the same exact fact. You did a different trajectory, but the fact is the same. Mm-hmm. Like theoretically speaking, you should take this into consideration,
Yes.
right? And then like putting in there in some shape or form.
Yeah.
I wanted to ask about like the REPL flow because from what I understood, it is not Jupyter-like. It's literally or just straight up REPL-like, where in order to output some text, you need to print it.
Yes.
Am I correct here?
Yes, exactly.
So have you thought about like leaving it like room? I don't know, to like write markdown or something like that. Because I come back to the grad student thing. Like if I had no room in my flow in order to write my thought about what I just saw, it kind of is a bit limiting. Like yes, I'm gonna like just engineer and do stuff, but at some point, like I'm not gonna write a print statement that has my thought in it. I would much rather just switch to markdown and just start to write it out. Like, what's your general intuition here?
So the interface that the model interacts with is super important. So like if it's a REPL or if it's a notebook with markdown, and it can also like plot stuff, like this is all really important. I think though the caveat here is that technically with the REPL environment, it is able to represent almost anything that the Jupyter Notebook can. So like, for example, if you want to store markdown, you could store it in a variable. It's silly, like it's not a natural thing to do, but it can do this. And I think when developing the paper, we decided like we want it to be as simple as possible. REPL is like the simplest possible thing. Let's just stick with that. But I think in the long term, like, you know, let's say people who want to use this in production or like want to squeeze out performance, yeah, it's a good idea. Like I think storing stuff in like a Jupyter style thing. There's another advantage of using a Jupyter Notebook. And also, the reason we didn't use a Jupyter Notebook is I think the REPL is just like really easy to set up. Like in, you know, the Jupyter Notebook, you have to do a bunch of stuff. Like if you were to write a library for this, it's a little bit nasty. But the other advantage is like, you know, in a Jupyter Notebook, you can print out images. You can like plot things. And there was this question earlier about like multimodal stuff. And the answer is like, yes, you can do multimodal stuff actually. The problem in its current form is like we pass everything around as text. Like we have no way of passing around images, but it's a really easy change like in the code. And I think one of the things, again, open research thing, if people are interested, is like multimodal RLMs or like looking at RLMs in multimodal settings. The reason this is so even more cool is like, I think code interacting with image stuff is like a very underexplored thing. And like how a model can interact with image stuff, or even like non-image stuff, but like generating images like plots and stuff, and using this like GPT-5, or they have some tools that let it do this. But I think like doing this in a more principled way is a super interesting topic. I am planning on adding support for this in the RLM library. If anyone also wants to add it themselves, feel free, open a PR. This is like a to-do. But yeah, I mean, the representation matters a ton. And this comes to like, what is considered in distribution, what is not. Like these are all important things, right? So
yeah, that was my thought, because like, because I have had this kind of grad student image in my mind.
Yep.
My thought was that like, okay, what does the data look in distribution? And the data look in the distribution for like analysis like this on long stuff, where you have to do some sort of like mini analysis about like the things. It looked like you have to look at like programmatically interact with the substrate, but then you have to think about it, right?
Yeah.
And say your thought, right? And then this become kind of the anchor that you use for the next step, and then like you do, and then you keep on doing this, so that like when somebody is gonna like you're gonna hand this to somebody, he's just gonna read like your thought, and then that's kind of summarization of all the code that is happening. But I mean, like inherently, the models, I've seen these Jupyter and seen this structure, so like maybe they're gonna be more pushed toward like the same kind of analysis behavior by being able to do that. I also like saw some research from Microsoft, I think, these guys, enhancing LM data analysis capability with notebook an inference time value gated. They're doing like a Monte Carlo search type of stuff. But basically, they're just literally trained the model to do data analysis with Jupyter style tooling, and it seems to be working well. So I don't know. It just sparked this this thought in general. Okay, so you did some ablation without subcall. Like in some cases, the RLM without subcall is able to perform better than one with like that can do subcall. So it's like, what's the issue here? It's like the RLM doesn't really know when it should be doing one or the other. Like, what do you think?
Yeah, I think it's a mix of things. One of them being, of course, like you said, it makes suboptimal decisions with the recursive subcall. This is also another reason why it's very important to add the baseline that you talked about before, like in the final version of the paper, because we do want to see, like, if you strip out the two most important parts, or like independently strip out one of them, like what happens. I think the one of the big points of that ablation is that, like, a really important part of this paper is not actually the recursion part, which is funny because that's the name, but it is really about like this offloading the context somewhere else. That is really, really important. I think another big part, sadly, is the noise. The annoying thing is, like, I will always criticize my own papers in this way, which is that I don't have standard deviation bars and stuff like this. Sadly, I just cannot afford to run, like with them. And so, like, I think in a lot of these instances, it likely is also due to some kind of noise, which applies even to, like, comparing to the other baselines as well. But I think, like, generally, yeah, suboptimal decision-making, noise, and then also the fact that, like, on the benchmarks where it does perform worse, these are ones where it actually can kind of get away with not using the recursive calls because those tasks are not very information dense.
True.
So it can just find the thing it needs, and then the main model can reason through what that information is. Like, it doesn't need to do the subcalls. So that's another explanation for, like, why there's a bigger gap for the other, for like oolong and oolong pairs. But yeah.
Okay, that makes a lot of sense.
Yeah.
Okay, so I'm gonna spare you the database question.
I mean, if you want to ask it, I'm happy to answer too.
But I mean, like, you just need to test it. I mean, like, how can we know?
Sure.
And I think this is, like, also adding some complexity to the system, which, like, I think it aligned with the other question, which is, do you think this could act as a replacement for, like, a full-blown RAG system? Like, if we push it to the extreme here.
I don't think so. The reason I say this is the usefulness of RAG and other retrieval methods is that, or a big part of them is that you pre-index stuff. Like, you pre-index, like, the things you're searching for, which is not cheap, right? Like, it's a big reason why we actually don't compare to RAG. I mean, also in our baselines, RAG just doesn't even make sense. Like, the only setting where it makes sense is a browse comp plus. But in their paper, they actually do RAG, and it doesn't do that well compared to BM25. Like, it just wasn't even worth doing. But I think, like, I still think there's value in methods that pre-index stuff. There is also value in equipping RLMs with tool calls and also equipping them with RAG as like as an extra thing. In that way, I think, like, RAG is still an important thing, or just retrieval methods in general are still, like, very relevant in specific settings, right? So, like, in settings, though, where I think where RLMs really shine is where, like, you cannot afford to pre-index, or, like, you're just given something new on the spot, which often happens for, like, a long agentic trajectory or something. But one of the things I do want to explore in the future is, like, a task where, like, the long context part actually doesn't come from the prompt. It comes from the trajectory itself. So you can imagine, like, let's say we have a really, really hard RAG problem, like a really hard retrieval problem, where you need to like piece together everything. I think Browse Comp Plus is an example of this, but maybe even harder, right? Like these like deep research style things. And like the model is given a retriever, like some kind of like either BM25 or a RAG thing. And so is the RLM. But the difficult part is like, as it retrieves more stuff, the trajectory gets really long. And it like in RLM actually is very well suited for this setting. And this is something like I think is actually really interesting to explore. And it goes back to this idea of like replacing a basic LM call with an RLM in your system and seeing what happens. But yeah.
Yeah. Okay. Yeah, that makes a lot of sense. Like, I also do think that like RAG still makes sense, unless you equip this thing also with the database and the RAG. Then like I mean like it's the difference is that with the RAG you have like just one shot type of situation, but in this case it's actually mining for the information, which is the part that is the most interesting. And like whether you add a RAG or tool call or like whatever library you want to add into like this system, like literally allow it to browse the internet and send an agent to browse whatever. I mean like this is just adding onto this core, a bit like the chain of thought is also doing tool calling and like going and doing this other stuff. It's just adding into the same kind of core.
Yeah.
There's an element that was interesting here, that there's a passing recursive LM output through variable for long output task. So if I understand correctly, it's offloading this to another subagent, right?
Yeah.
Subagent is doing a bunch of stuff and it has a prompt in it, whatever. It goes into the variable. It's not looking at what's inside.
Yeah.
To do the rest of the stuff. So it's saving a bit its context. It's kind of trusting that this is fine.
Yes.
Right? This is literally what's happening here.
So yeah, like you can imagine, this is actually a really cool part of this approach as well that I think is highly underrated. And actually Prime Intellect's implementation of RLMs doesn't even allow the model the model to produce a final answer. It has to output a variable string, and that is the final answer of the RLM. That is an extreme version of what this is describing here. So the point of this kind of this part of the paper is that basically another large limitation of large language models is their output context window, which doesn't get talked about a lot. Like there is a limitation; it's not infinite either. And one of the really cool things you can do with an RLM is you can also output nearly infinite or unbounded sequence lengths of outputs. And you can do this in various ways. So the trick that we use is basically the model can pick a variable and choose that variable as its actual output, as its final output. And this thing, like in the silliest case, right? You can imagine what it does. Like you give the RLM a prompt. It takes the prompt like as a variable. It passes that to a recursive model. The recursive model answers it, stores it in a variable, and then the RLM just outputs that variable. And that is the same as doing a model call. Like these are equivalent, right? But on the more powerful part is that like you can do, like for example, if your task is I have a 1 trillion token Excel sheet, and I want you to transform every row into like a new Excel sheet. The RLM can actually do this. It basically what it would do is it would chunk up the Excel sheet. It would spawn a recursive model on each chunk. It would save the output to a variable. It concatenate all the output variables into one final one, which is like maybe also 1 trillion tokens, and it'll output that. And this is very, very cool because it also mixes programmatic things. Like you don't have to use the language model itself to do the final answer. And this feature actually is what broke a lot of the benchmarks. Like basically the model, because it's so flexible, for example, like all of the, which by the way, I think is kind of silly, all of these benchmarks that are like, can a model do like 30-digit multiplication, right? And like sometimes the answer is no. And it's like, why are we even evaluating this? Like in this setting, like it will just compute it in a variable and output that. And I think you can do a lot of really, really cool things. Like you can, you effectively, like what the model can do in the REPL is form an entire like workflow of like how it's going to generate the final answer. And this includes both code and language model calls. So it's like almost building its own agent scaffold, like in itself. It's a very interesting thing. And it's part of the reason why oolong pairs is so hard, because oolong pairs asks the model to generate all the pairs that satisfy some property. And you can do this in a programmatic way using like this kind of passing the outputs to like across variables. So yeah.
I feel it's the right idea at the right time, because we already know that, like, I don't know, Opus 4.5, fantastic coding agent, whatever. Well, fantastic. Now you put it into a setup where the only thing he has to do is code, right?
Yes.
Like literally.
Yeah.
And like, okay, can't do 30-digit multiplication stuff. He can write the script to do it, and then it's done, and then you can just move on to the other task and just stitch it up. It doesn't have massive context, doesn't matter. It can spawn like 6 versions of it and just go and then run. So I feel like it's the right idea at the right time. There's this line that was I just wanted to get you like a rough idea. I know that you might be working on this right now. We hypothesize that RLM trajectory can be used as a form of reasoning, which can be trained by bootstrapping existing frontier module. Like, what will be the workflow here, you think, that you have in mind in order to actually do that?
Yeah, so this is actually really tricky in practice. But the core idea of what I was trying to say here was that, like, in the past, right? Now, I want to say this in a way that's like not confusing to people. So if people find this confusing, I can reframe the way that I say this. In this last year, the way that we have done reasoning models, like what is a reasoning model? A reasoning model is just a model that has been post-trained such that when it's given a question, what it will do is it will output this long reasoning trace, and this trace will also get fed back into the model, right? So it's like a form of conditioning. And given this reasoning trace it came up with and the original prompt, it will come up with maybe a better answer, like a more informed answer to what it was trying to do. And this is what I like to call reasoning in token space, because quite literally it is just outputting tokens to come up with an answer. And the way that these were trained, with RL, for example, although it doesn't have to be, is like you basically do this kind of version of like rejection sampling. I don't know if that's the right word, but like you get the model to produce these long sequences, and then if it gets the question correct, like you give it a positive signal, you do the update like this, yada yada. Like that's like it's simple, but obviously in practice there's a lot of like really nasty parts of it. But the reason why this works so well is like this is still the same as just training a model. Like you're just training a model with RL. And the sequence like is still fed back into the model. So this whole pipeline is the same thing as if you were to train it in a non-reasoning way. There's actually no difference for the most part. The difficulty though with the RLM part, which is why I think this is also so cool, is that the RLM trajectory is way longer than what fits into the model's context window. So you can't just naively train it the way that you would like. There's nothing to like the back propagation is really awkward here, or like even the reward is really awkward here. We now have a like, as we usually call in like the RL community, like a credit assignment problem. The other really weird thing is that we're not reasoning purely in token space. Now, if that's a confusing term, like I can explain it a little bit better, but we are reasoning in code and in token space. And not only that, we're reasoning across multiple model calls, which is really weird. Like it's a really awkward thing to do. And like how you actually train this model such that it never actually uses the full trajectory to train, like to do this like reasoning training thing, is kind of tricky. Like I think, I mean, it's an ongoing thing. We're looking into it. I also would be happy if Frontier Labs are interested in this as well. I don't care who ends up having the best model. I just want to see if it works. But
it could be you, man. It could be you.
Maybe. I guess that's kind of what that means.
Yeah. Have you thought about like evolutionary strategy here? Like, but I said this because I was talking to the egg roll guy, and then another researcher that is also working on this, and like it is comparable to doing like GRPO in some of the benchmarks. You just have to make sure that like you're doing it as optimized as possible, like on the GPU space. Yeah. But if you can pull it off, then like it doesn't matter what's happening in the middle. Like it can literally spawn like 100 sub agent, like recursively, whatever it is. You just wiggle the stuff right here, and then you look at the output, and you're like, this is good. This is we're gonna make it more of this and less of the other stuff.
Yeah.
One question I had, like, do you think that RLing or like whatever post-training the model for being an RLM will have an impact on the number of sub-agent being spawned and just generally their understanding of the task difficulty? So basically, like bringing Quen 3 closer to like GPT-5 level of understanding of like not being silly.
Yeah. So I would recommend reading, there's this paper called Context Folding something. I think it's like a ByteDance paper. They do something a little bit different than what RLMs do, but it's a similar core idea of like, we have multiple model calls and we want to train a model like with RL to be able to do this kind of thing. And they do a lot of like really interesting tricks like to the GRPL loss. And like, with the goal of like reducing the number of sub-agent calls, like reducing the length of the root language models, trajectories, stuff like this. My answer to this is it honestly depends a lot on like what your loss is. And this is just speculation, but I think that naively training with like how we've done it in the past, like with GRPO or maybe some other like modified version, is not going to work that well unless you have a lot of data. I think we are inevitably going to need to bake in some things, at least in the beginning. I think in the future, things will eventually just simplify out and maybe it will just return back to GRPO. I don't know. But I think for the time being, like, if we want to see some like initial cool results with RLMs, like we'll probably have to guide them in certain ways. Like, for example, if we want to post-train Quen 3, we kind of have to add a little knob that says like, hey, don't do that many sub-agent calls. Like, I think this is just what's going to happen.
Yeah, that makes a lot of sense. And I also had this other thought, but I think it goes into the same direction of like, if it knows that the task is easy or hard, it can decide what type of sub-agent it will call and like just use less compute. So if it knows that like this is a dumb task, it just doesn't want to do it, right?
Yeah.
Well, we can just like spawn a llama tree and then it's done, right? But if it knows that it has to do like big thing in here, GPT 5.2, like go for it. We're gonna wait 20 minutes. It doesn't matter because this is too complicated of a problem. Yeah. And then this thing can then orchestrate the rest. But here we don't know. There's a funny question on the chat. How does someone enjoy doing this all the time? Are you just sitting in your front of a computer all day? How is this fun? What's your take on this?
Yeah, well, so what I will say is I actually don't think I work that much. So I would say, now this might be surprising to some people. I think the hardest I've ever worked is during my undergrad. I genuinely think, and I joke about this a lot with my friends, like school can be hard. You can really make it hard for yourself. And I think like, but for me personally, like doing that was actually really helpful because I actually spent most of my time in undergrad not doing deep learning or machine learning stuff. Other than like research, I did do some like research stuff, but for the most part, like the courses I took were just like math or systems or like physics type stuff. And like that honestly built up enough of a foundation for me to explore, like, I think really simple idea. Like I think the RLM idea, for example, is really simple. I don't think it's like something like some crazy like novel thing. I do think it's quite clever. That's why I think it's like a little popular now. But I think in general, like honestly, I am not of the opinion that people should work like 15 hours a day. I think that's kind of crazy. But I do think just like if you enjoy it, like naturally you will just spend time doing these things, and I also think I've been very lucky. So I will say that too. I think things work out differently for different people. But for me, I would credit my successful streak of research ideas from when I started doing GPU mode stuff, which is really weird because it's not related to most of the research I do. But I think that's when I started like getting involved and seeing like what kinds of problems exist out there. So yeah, I think a lot of problems in ML are still like not low-hanging fruit, but more like there's a lot of clever ideas that haven't really been articulated very well. And I actually think the funny thing about this, like just AI stuff in general, is I don't think like we need crazy ideas. Like I actually think like a lot of ideas already exist and float around, but like the way that they become interesting is like when somebody formalizes it or articulates it in a way where people understand what's going on. I think Star, like Quiet Star and Star, which are basic, it's like Eric Seligman's work that underpins all the reasoning model stuff, is a great example of this. Like I think the idea of bootstrapping reasoning traces is not like, I'm sure many people thought of it at the same time or even earlier. But it's like his papers that made it clear to people that like this is actually a really good idea. And I think there's a lot of ideas like that are still out there. Some of them are rooted in, more like theoretically minded individuals, like people that like to think in math, and some of them are just like super simple. And so, yeah, I don't think there's any like secret recipe for these kinds of things. Like it really is just like you spend time in the field, and like I think these ideas just kind of float around. So, yeah.
Yeah. And also, like for those that are not aware of like research stuff, it's not necessarily like you just sit at the computer and look at the computer and like the idea will come from the computer. Like the computer is just for doing or like getting information, right? Like the idea, you need to kind of get an intuition and then like start to read a bunch of stuff. You can take stuff outside. You can just print your things and then just start to read it like out. You chat with researcher. In my view, like chatting with the researchers is the best way to kind of get to the core of it, right? Like you can read the paper, yes, it's all formal and stuff, but like getting like just the background intuition idea also give you some sense of like where the stuff is maybe going. So like actually like it's just a lot of chatting around. At some point you have to code something, right?
Yeah, of course. I mean, fundamentals are always super important, obviously. Like, and I think honestly, maybe this is a hot take, but I think the fundamentals for the AI field are like quite shallow. So like like if you wanted to get into pure math or physics research, it's quite difficult. Like it takes years to like, but AI, there's so much like to do. And I think, good ideas.
You can just verify it also.
Like, yes,
you can
so
just
easy to verify your results.
Like, okay, you have this dumb ass idea. You could just try it out, man. Like, let me know. Yeah. And then you'll see if it's worth it or not. If you need like massive amount of compute and it's gonna be super complicated, like realistically won't happen at all, right? So you just have to go and gravitate toward like less compute insane idea or get an internship at like OpenAI.
I actually think a lot of ideas don't require compute.
Same.
The funny thing is, I think all of the boring ideas require compute. Like in the sense that like it's the easy way out. Like it's sort of like, well, of course you can train on this stage, right? But there's a lot of like RLMs, for example. It does require compute, but the core part actually doesn't. And I think like there's really a lot of things that are missing currently. And these ideas can come from anywhere. Like genuinely, like you don't need to be like super established or things like that. Yeah.
Well, there's a good follow-up question on this. I think that would be the last one. How would one look for novelty when looking for research you want to publish? Somebody is studying their master thesis. Like, how do you get novel ideas?
So I think novel ideas come from understanding what's going on in the field really well. And that doesn't necessarily mean like reading 1,000 papers. Like there are some people that do that. That's great. I mean, I used to do that. I don't do that anymore. And part of the reason is I think, a lot of ideas get recycled, and I don't think that's a bad thing, by the way, either. But I think the way to think about this is like, once you read into a field enough, you will get frustrated with certain things. Like some things will just be like, this doesn't make sense. Like, why is it done this way? And honestly, the answer to that is usually like, because maybe someone hasn't explored it thoroughly. And it's not because like, oh, it's this way because it's the best. Like it generally is not true. I think like with what to pick, I mean, if you look at my history of research, it's like all over the place. Like it's genuinely like a bunch of random stuff. I am not like a specialist in some like in post-training, for example, or like I am not a specialist in context engineering. But I think it just tends to be that like as you just read into certain fields, like you will naturally have questions. Like Yassine had lots of questions for me today. And honestly, a lot of those questions are research projects of their own. Like they could very well be a thing to explore. And I think like oftentimes, like, so this RLM project started basically where I should give credit to my advisor, like very great guy, Omar. He's the guy that did DSPy. Like he basically was just like, hey, like, what if we look at like these models that basically like tool call other models? Like I don't know what would happen. Like let's just see what happens. And like initially we started doing a bunch of stuff and it did not work. Like it was very silly. It was like very dumb. And I'm sure a lot of people have tried it too. Before we settled on like the final idea. But I think like this is just like, it's things like that. It's just like, oh, like why hasn't this been done before? There are some subfields where this is a lot harder to do. So like systems, for example, it's a lot harder to pull this off because I think generally in systems, like it's not as much of a research question. It's more like someone needs to go do this and like you need to just learn how to do it. Flash tension is a great example of this. But yeah, I think like there's lots of great ideas to be discovered that are just
that's exactly it, honestly. Like, same here. Like I mean, at some point the ideas, you just have to like commit to one and like push it through. And it's really true. Like there are a lot of ideas, train of thought that have just stopped 4 years ago because the only guy that worked on it graduated. Right now working at McKinsey or whatever the heck, right? But it's not pushed, like not all direction in the human edge is being pushed at the same time. So what's next for this research direction and how can the community be involved here?
Yes. Okay. So this is important. The obvious next direction is training, right? And I don't think this is something that can be done that easily in the open, unless unless there is a community, like things like Eleuther and other stuff that have open compute and stuff like this, and like more centralized communities where they can train stuff. I think like a few companies, Primance like most notably is working on this now. Like just in general, can we solve a lot of the problems we talked about today? Through post-training, and can we get a model that is actually can boost its own performance by post-training on the scaffold? Very interesting problem. I think we'll see some results maybe in the next 6 months, maybe even earlier if some people are already working on this. I think another big direction, which is maybe the more open source part that I've been thinking about, is going back to this Jupyter Notebook thing and more broadly, like what is the actual like interface that we want to end up with? And I say this because I think that to make progress on this problem, like as a community, there needs to be some standards that are set. Like, I just think if everybody works on this like concurrently with different ideas of what to do, it's just gonna be a mess, because everything in ML is about being in distribution now, right? Like, let's just be honest. Like, for at least for language models, it's about being in distribution and trying to mold things in a way where the model likes to see like what you give it. And so I think thinking about how this is designed, like for this like open source library that we have, like this is super important. Number two is like this whole asynchrony thing. Like, we want this to also be really fast. And so I can imagine like in the near future, we might develop like another type of inference engine, but specifically for RLMs. And like how it deals with, like how it minimizes basically the longest depth of like chained language model calls, and like how we design these systems to be used on like your local server, and like how we design the sandboxes. Like, what is this REPL going to be equipped with? Like, what is it even going to be? Like, is it going to be a Docker container or like a Docker image that runs on your machine? Is it going to be like a sandbox, like you hook it up to modal, or like your own kind of cluster and like you do something like this? I think these are all open questions that do not involve a lot of compute, and that can be discussed and solved like in the open. And so I think these two things are super important. Number three, which I forgot about, is evals, which, going back all the way to the beginning, we need evals. Like, and I don't even mean long context evals. Like, of course those are important, but I genuinely think, actually, this is a great one. If you're looking for something to do, evals, like, you know, I think Swebench, I was fortunate enough to be there when John and Carlos and Ophir were like developing this thing. But like, genuinely, it just comes from like, hey, like, this is a naturally occurring problem. Can we get a model to solve this? I think we need more benchmarks like this, where models just don't do that well. And like, these are like, they try to reflect realistic tasks. And they will get hill climbed. That's, of course. But I think like, we need more diverse evals and things that reflect like, what do we actually want these models to do? Because I think actually that's probably the single most important driver for model progress these days.
Yeah, 100%.
Yeah.
No, I have nothing to add, man. Thank you very much, and also for staying like so.
Thank you for having
so
me.
long afterward.
Yeah.
Folks, go follow him on Twitter. Like, all the links are in the description. Read the paper; it's a really good one, also. And thank you very much, Alex, for coming.
Of course, thank you so much.
Honestly, I think like this. I really like the idea. I really do believe that it's going to be. It has the same characteristic that we saw earlier on with like a reasoning model. I think there's a lot of stuff to do with it. Like, they're just like the frontier here is kind of boundless. So if you want to get involved, this is a very good like type of shape to be involved, because you don't require training. You don't train these models, right? You set up the harness and then you tweak a bunch of stuff. So like, if you find these shape where like there's not a lot of like demanding compute, and it's about like kind of understanding qualitatively what's going on and thinking creatively about like how to set things up, it's a good place to start. The code is actually open source, so he has output it on GitHub. You can take a look at it, start to tinker about a bunch with it, and you're gonna have some ideas that then you can share with the community. And that's it for today, folks. I hope you enjoyed the video, and don't forget to check out the RLM video from Neural AVB Next for a more in-depth practical hand-on exercise. And have a great week.